I doesn't need to blow on it, it's just for the show. My cup is now full of liquid nitrogen. If you saw a little droplet on the table, they're not dangerous. This is dangerous, not a droplet. My styrofoam is a good insulin. So I can take my cup in my hand without freezing my finger. Cool. What happens is that if I take a sip out of my cup,
don't take it.
I'm gonna die?
Yeah, it's so cold. It's so cold, it's gonna burn your insides.
Yeah, for once it's too cold. And another reason, I said it's a compressed gas. If I take a sip, it's gonna decompress inside of me. Yeah. So if I drink my glass, yeah, I will be frozen inside, but my cup of liquid nitrogen will become gaseous nitrogen, so it will expand around 700 times. Do you think there are 700 glass cup? Do you think I can hold 700 cup? No. I will maybe explode. So I will use my nitrogen to cool my capsule down.
Oh, steamy.
Exactly. You know what this gas is?
Oh, what is it called?
Yeah, man, what kind of gas it is? The nitrogen is now evaporating, but we cannot see the nitrogen. It's invisible. This is water vapor, you see. When you're breathing outside in the winters, it's the same thing. You produce a cloud.
Cool.
As you can hear, my liquid nitrogen is boiling. My capsules are not hot. They are maybe 15 degrees. By our standards, this isn't hot, but by 15 degrees versus 200 below zero, there's a lot of difference in temperature. So the little bit of heat of my capsule is enough to make my liquid nitrogen boils. It transfers its energy to the liquid nitrogen. Once my nitrogen will stop boiling, it's gonna mean that my capsule are now the same temperature as the liquid. And then we're gonna see the superconductivity. As you see, I'm careful to not drop any liquid nitrogen on me. If I drop some nitrogen on me, what would happen?
It's
Gonna
gonna burn you.
burn you?
Are you crazy?
Yeah, a little bit, sometimes. Not,
What is wrong with you?
you saw my hand was wide open. It's to maximize the amount of skin that touch the liquid nitrogen. In small quantities, the heat of my body is enough to make a little bit of nitrogen evaporate, which form a layer of gas between my hand and the rest of the liquid. So by opening my hand like that, enough of heat was produced by my body to make enough liquid nitrogen to evaporate. If my glass was full, now it's empty, and I put my finger inside of it, a few seconds, my finger would cool down too much. My finger won't have enough heat to make the nitrogen boil and make this layer of gas to protect it. So at little quantities, it's enough. But inside of it, the flow is, there's too much nitrogen that go out. I need absolutely the glass. So what will happen when I remove the plank here? That will flow, and with a little help, it will fly over the rails.
Awesome.
So in fact, you see two things. First, the train is floating over the rail. Second, the train can follow the rails without falling down.
And how long does it last?
It will last as long as my capsule are cold enough.
My capsules, you guys, that's the superconductor that's inside. Will like it cools down the conductors so that it can make it.
What's happening is in the infinitely small scale. It's at the scale of the atom. So the magnetic field of the rail push the electrons at the surface of my capsule. The electrons that travel produce a magnetic field. So the magnetic field of the rail make the electrons at the surface of my capsule move, and then those electrons will produce a magnetic field that's opposed to the one to the rails. But my train is not becoming a magnet. I could take the train in my hand, try to stick a nail or trombone at the bottom, but the trombone won't stick. My capsule are not becoming a magnet, like if you take a magnet and a nail and you scratch it on the magnet, and the nail will become magnetic for a few times. It's not the same thing here. As soon as I take off the train from the rail, the phenomenon is stopping. My train absolutely need the magnet here. But the phenomenon is not perfect. If the superconductivity were perfect here, my train will float as well as North Pole magnet over another North Pole magnet. If I have two North Pole magnet, they will repulse themselves. But if I let go the one over, it will fall down. So here it's not the same thing. The train can follow the rails. It's because the phenomenon is not perfect. It's not all the magnetic field of the rail that is repulsed by the capsule. A little bit of it is able to enter the train. It's not much, but it's enough to hold the train over the rails. If it was 100% perfect, the train would fall, like a North Pole magnet over another North Pole magnet. When the train was floating over the rail, what was the only thing that slowed it down? It cannot be the friction of the rail. The train was floating over it. Air friction, exactly. So the only thing that slowed my train down was the air friction. That's why I needed to push my train a few times to give it enough energy to turn until my capsule were too hot to float. Do you have any questions?
How cold is liquid nitrogen?
Sorry?
Isn't it cold? Oh wait, but hot is
Almost 200 degrees below zero. But now they may be 50 degrees below zero. Do we use this technology to make trains? They have two different technologies to make trains levitate. The first one, we know it since the Second World War. In fact, we use electromagnet on the rails, electromagnet on the trains. If we produce a North Pole here and a North Pole on the train will float. Yeah, like this. To make the trains go forward, we're going to use another series of magnets. If we produce a South Pole in the front of the train and a North Pole here on the side, the train will be a pole. And we're going to do the same thing at the back. North Pole here, and the train will be pushed. But this technology is the same train that that is in use in China, the magnet. But there's a prototype run in Japan which use superconductors like this one. It's not exactly the same setup, but inside the train we're gonna have superconductors like here, but superconductive coils, not the giant capsule. The electricity will flow inside the coil, which will produce a strong magnetic field, and the magnetic field of the train will push the electrons inside another series of coils on the rail. The electrons, while circulating inside the coils, will generate in turn another magnetic field that will push the train. So my train, the prototype in Japan, will produce its own magnetic field on the rail to float. Yeah?
Wouldn't that be like dangerous for anybody wearing metal near the train or inside it?
A good question. In fact, a magnetic field loses its strength very quickly. Take a magnet and some nails. If you approach the magnet to the nails at 10 centimeters, it does absolutely nothing. You need to bring the magnet very close to the nails to see it stick. Same things with my magnet here. My train, I make my train float at this height, but if I double the height, the train will float but will fall down very easily. If I triple the height, the train won't be able to float because at this height, the strength of the magnetic field of my rail is not strong enough to hold this weight. Same things with super powerful magnet. In the MRI, you are inside the magnet. So the magnet are in its full power. But in the train, if this is the bottom of the train and you have the cab here, there's maybe 2-3 meters between the magnetic coil and the people inside. The magnetic field won't be strong enough to harm you. In fact, in the prototype in Japan, last summer, they make a run around the rail with the journalists inside the train. Journalists were filming and taking pictures with their electronic device. But straight on the coils, yeah, your iPhone will break down. That's
So if you drop something, it's kind of screwed. If you drop your phone, you're kind of screwed.
yeah. If you drop an iPhone, it will break anyway. Whether you drop it on the coils or
How about
not.
Nokia?
Oh. You have other questions? No? Okay.
How about
So, for now, you have 15 minutes, maybe a little more, to explore the floor here in the NAC. You can touch everything, take pictures, there's no problem. Later, my colleague Jean will explain you how we make paper and aluminum on the red bench. So if you're tired, you can sit down on the red bench on the other side. And after this, we're gonna go to the Shawinigan 2. The power plant you saw on the other side. So you have free time.